So last time was discussing the speed control of the induction machine, and in general we can use the scalar control. The meaning of the scalar control, as you noticed last time, we drive an equivalent per phase circuit, and from the per phase equivalent circuit we find a relation between the torque and the speed. Yes? So now I can control the speed according to that information. So this is what we call the scalar control of the induction machine, which is based on the steady state per phase equivalent circuit. Now, so this is the per phase equivalent circuit, and from the information that I can have from the equivalent circuit, I can find how to control, or I can figure out how I can control the speed. Now this is the, let's say, the plot of the torque speed characteristic. Now let's assume that the machine was operated at this point, and for any reason I need to change the speed. What I should do? Now remember, this curve here is for certain voltage, certain frequency, correct? This one for, let's say, V1, F1. And I'm having here what? I'm having here a load. So this is the operating point, yeah? Let's assume that I need to operate the machine here or here. What I should do?
Change the voltage, frequency.
So I need to modify the torque speed characteristic of the machine, correct? I need to do a modification such that the intersection point appear here. Yes? If I'm willing to operate at this point, I need my intersection point to be here, yeah? If I need to operate at point B, let's say here, I need to modify the operating point or the torque speed characteristic such that the intersection will be where? At the operating point. So what I need to do a modification, correct? So now let's see what kind of modification I can do. Now this is what? The torque speed characteristic that we got from where? From the bare phase equivalent circuit, yes? Now, how I can control the speed? The first one here, if I look, what variable I'm having? Here is the frequency, correct? So the first one is what? Changing or the number of the poles, then the frequency. So changing the number of the poles. So simply this means that I can use a special type machine in order to change the number of the poles. Yeah? The second one is what? The frequency. This is the frequency. What else?
Voltage.
The voltage. What else?
R2 if it's one rotor.
R2? The RR dash, you know, the rotor. Yeah? This is only valid for what?
One rotor.
For the one rotor. This only option valid for what? For the one rotor. And the final is what? Is the varying the voltage. So simply here I'm having what? Either I'm modifying the machine by changing the number of the poles, and this is not an option for a commercial machine, which means that you cannot find a commercial machine, industry machine, that will allow you to change what? The number of the poles. It's not easy. You need to reconfigure the windings in order to change the number of the poles. The second one is varying what? The line frequency. How we can change the frequency, or how we can vary the frequency. If I'm using a transformer, can the transformer change the frequency? No. So what I need power electronics, correct? I need power electronics in order to change the frequency, which, let's say, a converter can change the frequency.
Voltage source inverter.
The inverter, yeah? The voltage source inverter. In general, there's a current source inverter and there's a voltage source inverter. The most common one is the voltage source inverter. Yeah? The input is what? Is voltage. Yeah? Or simply, we can assume that the inverter is a variable voltage source. Yep. Okay. Now, the inverter. If we recall from the power electronics, I need a pulse width modulation, or I need, let's say, a gating in order to what? In order to convert the DC power to the AC power, correct? Now, in the power electronics, which method you did the study?
Bipolar, PWM, unipolar, PWM.
I think you studied the pulse width modulation and the 120 degree.
120.
Yeah?
120.
And 180 degree, correct? Yeah? Correct? So those can change the frequency?
Yes, depends
Yeah.
on the reference.
They can change the frequency, correct? So we need what? We need an inverter. Yeah? We need an inverter. Good? In order to what? To change the frequency. For varying the voltage, although I can use a transformer, but no one will use a transformer because transformer you need what? A human power in order to change it. I need what? Also a power electronics. Yeah? In order to change what? The voltage. For the external resistance, this only option valid for what?
1 watt.
For the one rotor. Huh? For the one rotor. So now, changing number of the balls. The machine must be special manufactured, which is a special purpose machine. This cannot be found in the market for industry purposes. Yeah? Only used with a squirrel cage motor. And this is only a discrete change in the speed. It's not recommended to be used. Yeah? Now for the variable voltage, if I'm only considering I'm adjusting the stator voltage while keeping the frequency. Yeah? So in this case I can use what? I can use AC voltage controller, which is the anti-parallel thyristor, or what we call triangle. Yeah? Here only what? I'm changing the RMS value of the voltage, but I'm not changing the frequency. I'm not changing what? The frequency. Now let's see. From relation between the torque and the speed, we know that the torque is proportional with Vs squared. Here I'm changing what? I'm changing only the voltage. So I'm assuming all the other parameters are kept what? Constant. Yeah? So from here I can see that the torque is proportional with V squared, correct? Yep. So simply now if I'm reducing the voltage, what will happen to the torque? It will be reduced, correct? Good. So simply, if I need to adjust the voltage, it will be adjusted as a fraction from the rating. Let's assume it's B, a factor. So B is what? Less than 1, because it's not possible to impose a voltage higher than what? Than the rating, correct? So if this modification is done, then this will be what? The rated voltage. Yeah? So here, I'm assuming that Vs is equal B Vs rated such that the B is less than or equal to 1. Yes? Yep. Good? Good. Now, if I'm plotting the curve, last time we did plot the curve, we stated that from this relation, TE is a proportion with Vs squared. Also, we know that Tm is a proportion with Vs squared. Yeah? We also know that T start also is a proportion with Vs squared. So last time we said that if I'm changing or if I'm reducing the voltage below the rated value, I'm shrinking the curve. Yeah? I'm not changing the no load operating point or the synchronous speed, because the synchronous speed is already directed to what? To the frequency, to the line voltage frequency, Fs, correct? So simply what I will do, I will shrink the curve. Huh? So what I will do, I will shrink the curve. So simply, if I'm replotted here, if I'm assuming that this is the rated value, now S max, it will be the same, correct? So simply, what I will do, I'm shrinking the curve. Yeah, I'm shrinking the curve, and this curve by reducing what? Vs, correct? Direction of what? Of reducing Vs. So now, if we assume that this is the load that I'm driving, in this case, I'm controlling the speed of the load from point or from here to here, correct? Do you see after this point I cannot go? This is actually I'm reaching the maximum, the mean, which is what? The limit of the stable region. After that, the machine will become what? Unstable. So simply, this means that I'm controlling the speed in what? In a narrow region. Yeah, in a narrow region. And sometimes I will have problem in starting with the machine. So that's why we say that B is restricted to be greater than 0.5. Yeah. So for in general, it's recommended to have B greater or equal 0.5, less than or equal to 1. Yeah, in order to have, let's say, speed control using the stator voltage control. So simply, the first thing, as we said, we have a limited speed range. The second thing, now at low voltage, we will have what? High starting current. Yeah? If we have high starting current, this means that we have higher copper losses. Yeah? And the second thing, if we only using the stator voltage control, then the power factor of the machine will be poor, and in the end of the day, actually, the shape of the current will be distorted. Now, simply, if we replot here the output of the voltage control. Now let's assume that here I'm having the voltage control. Which consists of track or antiparallel thyristor. And this is the induction machine. If we use a speed control, let's assume here I'm having a tacho generator. Now here I will compare, let's say, the speed with a reference speed, then I'm using, let's assume, a controller, a speed control, and after that I will give the firing angle, correct? Yeah? So if I'm taking a pair phase, and let's assume here I'm having a load, and this is Vs, and this is the Vr. Now here I'm having two thyristors here, T1 and T2. If I need to fire the thyristor, the first one, let's assume that this is the voltage, the supply voltage. Now T1 will be fired in the positive half cycle, and T2 will be fired where? In the negative half cycle. So let's assume that I'm firing at this point. This is alpha. So here it will be what? Alpha 2. Huh? So what will happen here for the voltage? If I'm assuming continuous operation, yeah, it will be something like this, correct? Let's see. Control E it was. Yeah. Something like this. So if we assume that we are firing at alpha 1, then this would be the positive cycle. Then, if this will be the extension point, or let's assume discontinuous operation, then this would be the negative half cycle. So plus minus here. Now what I'm changing the area, so I'm changing the RMS value. Yeah. So now here the voltage will be distorted. So if the voltage is distorted, this means that it will be a higher harmonics, and also this system will have a poor line power factor. In the end of the day, the power factor is the relation between what and what? Between the current and the voltage.
Mm.
And higher power factor, this means that I'm having what? Why actually we are, let's say, concerned about the power factor? Simply, if the power factor is close to 1, this means that all the input power is actually an active power.
Mm.
Yeah? The power that's converted to a mechanical energy. Correct? Yes?
Mm.
Yeah? This is one. The second thing in the industry, they are forced actually, yeah, to regulate the power factor or to correct the power factor. Otherwise, they will pay extra money for what? For the generation and distribution, let's say, company, correct? Yeah, because this will put stress on the network.
Mm.
This will put stress on the network. So in general, we are not using the variable voltage, using the, let's say, the thyristor voltage control.
دكتور هاي المنطقة اللي بيكون فيها الفولت زيرو، ليش الفولت زيرو؟ مش المفروض
Now, if I'm assuming discontinuous,
yeah, okay.
this is if I'm assuming discontinuous.
طب هو مش في العادة continuous في حالة الاندكشن مثلا؟
It depends on the, of course, for the drive, for the machine, it will be continuous. For the machine, it will be continuous. So if this continuous, this will be the scenario. Okay, then here, this will be a negative cycle. Now this is the extension, huh? Because I'm having the inductance, so this will give friction here. Yes. Then let's see, put it here. So if we assume a discontinuous mode, we already proved that. If we assume continuous mode of operation, then at the positive half cycle, I'm firing T1. So this one is on. So this voltage will equal to this voltage, correct? So this is the supply voltage. And let's assume that I'm firing the T1 at the positive half cycle. So what I can see is the voltage here. From this point and here. Yeah? Now after that, what will happen? The inductance here will change property because the current now is reducing, and this will do what? Extension. Yeah? Doing the extension, so until this point. Now after that, I'm firing the second switch at the negative half side. Let's assume it's here. Yeah? So now, according to the, now it will take the negative value. It will be, yeah, the voltage will be like this one, but the current will be continuous. The current will be continuous. So this is the I, the current will be distorted, and this is the V. Assembly, this is will be used for low efficiency machine, such as, let's say, small fan or pumps. Now, what about if we need to vary the frequency? If we need to vary the frequency, let's assume that I need to control the speed above the rated speed. In this case, the frequency will be increased. If the frequency increases, what will happen? Now, if I'm only controlling the frequency, the voltage will be what?
Constant.
Constant. Should be constant because I'm changing only one value. Huh? So the air gap flux will be decreased or reduced?
Decrease.
The flux will be what?
Decrease.
Decrease. Now, simply, this is very simple, by the way, if we recall the per phase equivalent circuit. This is Vs and this is Em. Now, we stated that if we neglecting the drop voltage across the stator circuit, then simply we can say Vs or Em is almost equal to what? To Vs. No? Now the current here equal to what? Im. Im equal to what? You say that it's Em over Xm, correct? Or which is almost equal to what? Vs over what? Xm, yep? Yes? Now let's see. Xm is equal to what? Xm equal to what?
Given.
Yeah, Vs over 2 pi, yeah? Fs Lm, correct? Yeah?
Yes.
This is equal to what? Im. If I multiply here by Lm, what I will get? Yeah, Vs over 2 pi Fs, yeah? This is actually what? Lambda. Do you remember lambda? The flux linkage equal Li. Yeah? And the flux linkage has a relation with what? With the flux. It's N multiplied by this one. Huh? So the flux is equal to what? N multiplied by lambda, correct? So now what I'm doing here, I'm increasing what? The frequency. So simply if I'm increasing the frequency, the flux will be what? Will be reduced. If I'm fixing what? If I'm fixing the voltage. Okay, if I'm fixing what? The voltage. So now the developed torque will increase or decrease? Actually, it should decrease. Huh? If I go to the per phase equivalent circuit and discuss the relation, it will be inversely proportional with the frequency. Yeah? The second thing, I'm reducing the flux. Yeah? And the flux actually is the main component of the torque. Yeah? Do you remember in DC machine? In DC machine, actually, the torque is proportional with the product of two fluxes, the armature and the field, correct? Yeah? Yes? Later on, we translate it to be what? A relation between the torque and the current. Yeah? Here are the same. If I'm assuming Lm is constant, this means that it will be what? Related to the current. Huh? So the developed torque will be decreased. So this is the relation. This is the torque. And now here I'm increasing the frequency by what? By B. And B here is greater than or equal to 1. Less than what?
certain limit.
B max. In the end of the day, I'm having a maximum speed. So now, what I'm having here, why I'm adding here B, and why I'm adding here B squared.
الأوميجا S اللي هي 2 by F.
So this one is what? The rated. Correct? Yes? And those are what? The inductance calculated at the rated frequency. Correct? In general, any, let's say, problem is given according to what? To the rated frequency. I'm giving you certain inductance. X1, X2 equal, for example, 3 or 4 ohm. Those calculated based on what? The reactance should be calculated based on a certain frequency, correct? So in order to use the rated reactance, in this case here I'm using what? B squared. Or otherwise, you should calculate the inductance. Then recalculate the new reactance, correct? And this will be a time consuming, this will be more straightforward. Now let's see. If I'm changing the frequency above the rated, the first thing I will change is what? The node speed, correct? It has a direct relation. And S equal to what? 120 F over P. So now I'm increasing F, so NS will what? Will increase. Correct? Okay. Now what will happen to the maximum torque?
Decrease.
It will decrease, correct? Do you remember the maximum torque?
Yes.
Yeah, so it will be decreased.
3V.
And the starting torque also will what? Will be decreased, correct? So now, what we have? So now, if we need to control the speed below the rated speed, so let's assume this is the rated speed. If I'm controlling the speed here, and this is the rated, or the base speed. If I'm controlling the speed below the rated speed, I will use what? Voltage control, correct? If I'm controlling the speed above the rated, I will use what? Frequency control, or what we call flux weakening. You see, I'm weakening the flux. Now, what about if I need to control the speed from low speed to higher speed? Or what about if I need to enhance the efficiency of the speed controller at speed below the rated speed?
Change V and F.
Changing V and F. Why? Now, do you remember when we change the voltage alone? If I'm changing the voltage alone, what will happen to the flux? We assume that this one, the flux, in the end of the day will be proportional with what? Vs over the frequency, correct? You see it? From here on. Later on, I will derive this one. Now, in the voltage control, I'm reducing what? The voltage. So the flux will be reduced, correct? In the frequency control, what I'm doing? Increasing the flux, so also increasing the frequency, sorry. So the flux will be what? So reduced, yeah? So what about if I can manage to change the voltage and the frequency such as the ratio in between is constant, fixed at the rated value? This is good for the machine?
Yes.
Yes, in general, the machine is designed to operate at what? At what? At the rated value. The best condition for the machine is what? Is the rated value. And this is the idea behind the constant volt per hertz control. So, as we stated that the flux in the machine is actually proportional with what? With the voltage and the frequency. Of course, this is assumption that I'm neglecting the drop voltage across the stator circuit, correct? Yeah, I'm assuming that RS and LS is very small, such that the drop voltage across the stator circuit is negligible, correct? So now let's see. If I need to control below the base speed, then if only the frequency is reduced at rated, then the air gap, what will happen here? Now let's see. Someone will say, I can control the speed of the machine below the rated speed by controlling the frequency. For example, if the frequency is 50 Hertz, I will put it 40 Hertz. Yeah? So logically, this means what? The speed will what? Will be reduced. This assumption valid? This method is valid? Yes. Who agree with that? Did you understand my question? Is reducing the frequency while keeping the voltage constant is a valid option? Someone will say, I can control the speed below and above the rated speed only by changing the frequency. This is very nice. We know that omega is equal to pi f. So reducing the frequency will reduce the speed. Increasing the frequency will what? Will increase the speed. Is this valid option? Ali said yes.
حسب الباور الكترون.
حسب باور. No, not valid. Why?
بصير في losses كثير أو شيء.
Why? Now let's see. Do you remember the pH curve?
هسا بتزيد الفلكس تيار.
Yeah. The life is not easy like that. Huh? It's not linear relation. So simply if we recall the pH curve or I lambda curve, the same, huh? I lambda curve. We know that H is proportional with the I, and B is proportional with the flux, correct? I lambda curve. Now, the ideal case, I'm having a linear relation, but this is in real life. It's not. What I will have a nonlinear relation which is saturated. Yeah. Now, what will happen if you are increasing the flux? Simply, this means that you are consuming more current than you need. Yes? Yeah? So if you are consuming current more than you need, this means that the portion of the current that you don't need is actually lost. Correct? Yeah? So due to saturation, I cannot go in the frequency less than the rated while the stator voltage is constant. I cannot do that. Why? Due to what? Saturation. It's not optional. This will generate a core losses. Huh? Core losses. Hysteresis losses. So simply, if we reduce the frequency while Vs is kept at constant, then the air gap flux will be saturated. Huh? The meaning of saturation what? I'm consuming more current than I need, which means that I'm increasing the losses. So, what option I'm having? What about if I can keep the air gap flux to the rated flux? The best scenario for what? For the machine is the best condition. How we can do that? Simply someone will say, if you are reducing the frequency, also reduce the voltage in the same factor, such that the ratio in between is what? It's constant. Yes? And this ratio is what? What we call D later on will be what? Vs rated over Fs rated. So now let's see. In this case, the maximum torque, if I put it here. Now, do you remember the first assumption that I'm assuming that the R1 and Ls is negligible, correct? If those are negligible, then simply this is 0 and this is 0, correct? Yeah? Now, here I'm changing the voltage and the frequency in the same factor, correct? So simply this can be seen as what? This can be seen as B, V rated, squared, and here squared, correct? Yeah? Over 2 if I'm using the rated values. And this will be what?
B.
B
Square.
x, no, it's square root. So x
Okay.
at rated value, correct? So this will be x2 actually, because already we assumed that L1 and R1 is what is negligible, correct? So now those B's will all eat those B's, yeah? And I will end up with what? That T max actually is proportional to what? V rated squared over F rated, correct? Yeah? So it's constant. Yes? Correct? It's constant. So someone saying that I can use instead of F omega, it will be the same. The factor is 2 pi. Yeah? So this means that if I need to plot the torque speed characteristic, then the maximum torque I can keep it constant. While the slip is changing by the way. Yeah? So if I need to plot that, it will be something like this. You see the maximum torque is constant. Of course, this is under the assumption that what? I can neglect the drop voltage across the stator field. Correct? Now, I will have problem where? At low speed or low frequency. Why? Now, at low frequency, this means that B is low, correct? V1 equal B1, let's say Vs. Huh? Let's assume that now I'm imposing what? 0.1 Vs, 0.1 of the rated value. And the drop voltage across the stator, let us, roughly speaking, let's assume that I need to impose 10 volt to the stator. And the drop voltage is 1 volt. So in order of magnitude, 1 volt compared to 10 is too much. It's too much. Yeah? So that's why at low speed or low frequency, I cannot neglect the drop voltage. So if I cannot neglect the drop voltage, what I can do? I can boost that voltage. I can say I can calculate how much drop voltage I need. Then instead of imposing 10, I will impose what? 12, such that in the end of the day, the gap will be what? Will be constant. Yeah? So this is the idea behind the boosting. The first one here, I can add delta B at start. Or someone will say I can use nonlinear offset, which is vary according to IS. If I know IS, I know the frequency, so I can calculate delta Vs, yes? Yeah? If I know the stator current, and if I know the frequency, I can calculate delta Vs. Delta Vs equal to what? IS multiplied by ZS, correct? Yeah? And ZS is equal to what? RS plus JXS, correct? So if I know the frequency and if I know the current, I can calculate how much voltage I need to impose in order to compensate of the drop voltage. Someone will say, this one modified the relation, by the way. Here I'm having what? 3 lines. Yes? The dashed line here represents what? This is the constant V over F. Yeah? This is the constant V over F. Now this one is the modified V over F according to linear offset. I'm boosting the voltage from 0. The nonlinear line, this is the V over F using what? Nonlinear. Which one more accurate? The nonlinear, correct? It's almost from here. It will be what? It will be capturing, let's say, the constant V over F. Yeah? Someone will say, why are you doing that? Simply, it's very straightforward to specify minimum frequency, F minimum, and this will be F rated, such that between the F minimum and the rated, the relation will follow the constant V over F. Correct? Now, the frequency less than the rated, fix the voltage. Or simply restrict the inverter not operating to a frequency less than F minimum. Yeah? So now between the minimum frequency and the rated frequency, the relation actually is what? Is the constant V over F. So the flux is what?
Constant.
Yeah, constant at the rated. Now what about if the frequency higher than the rated? What will happen? Now this is the plot between the frequency and the voltage. Huh? So what will happen?
We can't increase V over the
So simply this means that the voltage will be constant. So now this pointing toward where? Vs rated, yeah? So now this relation actually contain what? Contain the constant V over F, and this one is what?
Variable F, constant V.
Frequency control.
Frequency control.
So this one is what? F control. And this is actually V over F control. Yeah? And this here, the modified or the boost V over F control. Yep. Yes? So this is, I think, more straightforward than those. This one will give you from the minimum to the rated value the actual V over F control. Above the rated value, you are going automatically to where? To the frequency control. So now let's see how we can translate this one. So the first thing here, we assume that we are modifying the frequency by a factor B, and B can be greater than or equal to 0, less than or equal V max. So here I can control the frequency from B minimum, let's say, yeah, which is related to F minimum, yeah, to the B max, which is related to what? To the F max. Then for the stator voltage, it will follow like follow. If the frequency less than the rated, then I will use VS rated. Yep. If the frequency above the rated, I'm fixing what? I'm fixing the voltage. Yeah? Such that the ratio between the voltage and the frequency kept constant if B less than or equal to 1. Otherwise, I cannot keep it. If B greater than 1, can I keep this one? No. This D, which is the ratio between the voltage and the frequency, is kept constant if and only if B is less than or equal to what? To 1. Above that, I cannot maintain this relation. Huh? I cannot maintain this relation. So, for operation at frequency B, let's say, what will happen here? Here I'm adding here B, so that I can use the rated speed here. And here I'm adding B square, so that I will use those what? The reactance calculated at the rated value or rated frequency. So simply here, if I'm assuming that I'm increasing B greater than 1, correct? Yeah? So do you remember the curve that we are plotted here? I'm here, huh? So at this point, the voltage will be what? The rated. So the V over F now is already including what? The frequency. But I cannot say it's V over F. After F rated, it will be converted to be what? Frequency. F control. Now, what will happen to the S max? S max the same, it will be what? Reduced. Correct?
Mm.
What will happen to the V max? It also will be reduced. Correct? This, if I'm controlling the frequency what? Above
Right.
the rated frequency. So if I need to plot the VF control below and above the rated frequency, now below the rated, let's assume that this is the rated frequency. Here I'm having what we call the constant torque area. Do you remember? At V over F, T max is almost what? Is a proportion with Vs rated over omega S rated. Yeah?
Mm.
So it's constant.
Mm.
Yeah? Above that, I cannot hold the torque. The maximum torque will be reduced. Yeah? The speed will increase. The no load speed will be increased. Why? Because I'm increasing the frequency. So this and the flux will be reduced. So that's we call it what? The field weakening. In the case of F, is higher than the rated value. And this region is called constant power region, and this region is called constant torque region. Good. So simply here, this is a relation. Now, in the constant V over F, the flux is what?
Constant.
Constant. So here I will try to keep the slip constant at the rated value. If I'm keeping the slip constant at the rated value, then the efficiency will be what?
Same.
The highest efficiency.
Mm.
The machine actually is designed to operate at the highest efficiency at the rated condition, correct? Yes? So simply here, I will keep the slip and I will regulate the current such that the slip is constant. Until I'm reaching where?
Afraid.
The F rated. After the F rated, I cannot maintain the ratio between the voltage and the frequency to be what? Constant. Yeah? And the voltage should what?
Constant.
Should be constant, correct?
Mm.
Now here, if I need to regulate the current to be constant, then the slip should be increased. Yeah? And the flux will be reduced. Why? Because here I'm keeping the voltage constant, I'm increasing the frequency, so the flux will be what? Reduced. If I need to maintain the current constant, I cannot do that unless I'm allowing the slip to what? To increase. Yeah? Yep. So again, this is what we call the constant power region, and this is what we call the constant torque region, sorry.
Mm.
And this is what we call the constant power region.
So في F max.
Yeah, there's F max. And F max is either related to the omega max mechanical or to the inverter maximum frequency.
Mm.
Now, in general, I need what? I need inverter in order to control the amplitude and the frequency of the AC signal, correct?
Mm.
Now, the input for the inverter is what?
These.
DC. And the output is what? Is AC, correct?
Mm.
Variable voltage, variable frequency. Yeah? Now, either this inverter, for example, can adjust the frequency from F minimum to F max. So in this case, the maximum frequency is controlled by what? By the inverter. In the end of the day, you cannot change the frequency without the inverter. Or, if the inverter allow arbitrary frequency, then F max is related to what? To the maximum speed that the shaft can handle. Yes? In general, for us, I will restrict it to be the maximum frequency that the inverter can handle. So I will tell you that this inverter can provide a frequency control from 5 Hertz until 100 Hertz. In this case, F minimum will be what? 5. And F max will be what? 100. Yeah. Good.
والدكتور إلها دخل بالمينيمم فلكس للماشين بيقدر إنه إحنا بنزيد الفريكونسي.
Now, see, if we notice that, if we replot the torque speed curve, the FV curve or the in the constant V over F and above the rated frequency. If you notice, we specify 3 key frequencies. The first one is the F minimum. The second one is the F rate. The third one, F max. Now, F minimum here, either it can be seen from the frequency or the speed that I cannot neglect the drop voltage across the circuit. In this case, I need to boost the relation. Yeah? This one. So here, I need to boost the voltage. Yeah, by delta V. After that, the relation will follow the V over F constant. Correct? After that, I will enter to where? To frequency control. Yep. Good. So now, this one and this one either is given from the converter capability. The converter, for example, this voltage source inverter can provide you F between, let's say, 10 Hertz until 200 Hertz. So F minimum is what?
10.
And F max is what? 200. Good. Now let's assume that the machine, I'm connecting here a machine, and the machine has 380 volt, 50 Hertz. Yeah? At F equal 10 Hertz, the voltage equal to what?
10 هرتز 380
هي الدلتا في.
Yeah. So simply I need to maintain the ratio D, remember D, which is the 380 over 50 to be equal to V over 10. Yeah? So simply now V is equal 1 over 5 multiplied by 350. Yes. So this one I know it now. This value. Yeah? Now this value equal to what here? 50 Hertz, and this will be 380. Yeah? Yes? So this will be 50. This will be 350. This will be what? F minimum? 10. And the voltage here we already calculate to be 380 over 5. What about F max equal to what? 200, thank you. And the voltage?
Constant.
Yeah, 380. Yes? Good. So now, if I know the frequency and if I know the voltage, can I generate or can I control the inverter to generate the needed voltage and the frequency?
Yes.
Yes, using the pulse width modulation. I will give a reference signal, I will compare it to a carrier, then I will generate the gate pulse for the switches. Yes? Good. Now, do you have any question here for this one? No? No, huh? Okay. So if I need to implement the constant volt over Hertz control. Now we have open loop and we have closed loop. This one is open loop or closed loop? the control signal, yeah, has no relation with what? With the actual output. We are giving what? A certain reference. Yeah? Now, if I need to control the inverter, I need to generate what? A reference signal. And any reference signal should contain what? V max reference and frequency reference, correct? Theta reference, correct? Now, this will come from where? From the V over F. I will replot it here. If I'm giving you omega star, now someone will say, wait, you are plotting the curve between F and V. I say, yes, multiply here by 2 pi. This will be between omega and V.
Yeah.
It will be the same thing. Yeah? So there's no restriction if I'm plotting for respect to F or if I'm plotting with respect to omega, because there's a ratio. Yeah? So if I'm giving you omega, then what you will use? The curve that we already agreed that this one will fit the V over F control. So this will be a relation between omega and the voltage, correct? So this will be what? Omega minimum. This will be what? Omega rated. And this will be what? Omega maximum. The output of this block is what? If the input is omega reference, then the output will be what?
Voltage.
Voltage reference, correct? So this will be Fs reference. Now someone will say, this can be line to line, this can be phase, this can be RMS value, this can be maximum value. I don't care. In the end of the day, I need only to understand, is it maximum? Is it RMS value? Is it phase? Is it RMS? Why? Because the reference will be what? The RMS phase voltage, correct? Yeah? But if the relation, for example, between omega and the line-to-line RMS value, in the end of the day, I will take this one, I will multiply it by square root of 2 and divide it by square root of 3. Yes? It will be the same. So, let's assume that the output from here is what? Vmax. That I need. This signal, yeah? The output from here is what? Is this signal. The meaning, huh? The maximum rated value. Yeah? Then, if I need to complete the reference, I need what? Theta. So how I can get theta?
Integration.
Yeah, simply, if I take this one here, if I integrate it, let's say the integration, I will not use 1 over S, because S in general for the slip in the induction machine. And this will be what? Theta star. Now, I'm having V S star and theta star. I can build what? VA reference. The B and the C is shifted by what?
120 degrees.
By 120 degrees. Now, after that, I should give those to the inverter. Yes?
Yes.
Yeah, but how I can do that? Now remember, from here to here, this is what we call the low power circuit or the control circuit, correct? And from here to here, this is what? The high power circuit, yeah? Or the power circuit, yes? This is the power circuit. So actually, I need here a mechanism in order to tilt the inverter to fit the needed voltage to the motor, yeah? Yes? How we can do that?
Comparators, gate drivers.
Converter and inverter. So simply, let's see. In the first sense, the inverter, let's assume that this is the inverter. This is the plus, this is the minus, and this is VDC. Here I'm connecting phase A. Here I'm connecting phase B. Here I'm connecting phase C. So this is the A, this is the B, and this is the C. Now each switch here is actually a power switch with anti-parallel diode. Correct? Yeah? Okay. So here, in order, if you don't like to remember 1, 2, 3, 4, 5, 6, and so on, For me, I prefer to call it the higher switch of phase A, the lower switch of phase A. So this will be what? The higher switch of phase B. This will be what? The lower switch of what?
Phase B.
So this will be what?
Minus C.
Yep. And this will?
This is low.
Thank you. So now this will be leg C. Yeah, thank you. It's C. So this is the B, this is the C, this is the B, this is the C. Okay? So this will be leg A. This will be leg B, and this will be what? Leg C. So now leg A gate pulse is generated from A reference. Remember, we constructed the three references. The first one is VA reference, which was to be square root of 2 VS sine theta star, correct? And we have VB reference, which is shifted by this one by 120 degrees according to the sequence. And VC as a reference, which will equal square root of 2 VS sine theta star plus 2 pi over 3. Yep. So now let's see. If I need to generate the gate pulse here, I will use a pulse width modulation, which means that I will compare VA with what? With a carrier. So this is the plus, this is the minus, and this a carrier. Do you remember the pulse width modulation in the case of the tuba? It's almost the same. It's almost the same. Yeah? But simply there VC was constant. Yeah? In the DC drive system, in the end of the day at steady state, VC will be constant. Yes? Here, at steady state, VA will be alternating. It's AC signal. Yes? Has magnitude and angle. So, good. So I will compare what? I will compare the reference with a triangular or a carrier. Now, any triangular will have what? An amplitude and a frequency. Yeah? So V triangular and F triangular. Then I will say that I will generate the gate pulse for the higher switch A such that if VA star is greater or equal to V carrier, then the switch will be 1. Closed. And if VA star less than V carrier, then the switch will be what? 0. Yeah? So this is what we call the carrier signal. Yep. So we know that any leg should obey SHA or I, let's say, plus SLI should equal to 1. Yeah? When I is equal 1 or A, A, B, C, or C. Yeah? Well, okay. Yes? So simply this means that the two switches here will be in the complement state. If the upper switch is on, the lower switch should be what? Off. Otherwise, I will do short circuit, or what we call shoot through. Yeah? Circuiting current. Short circuit. So simply someone will say this means that I need to do what? Inverted here, and this would be the lower switch of leg A. Yep. Yeah? So simply this is how we can what now? Generate the gate pulses for the leg A. If I need to generate the gate pulses for leg B, what I will use here? Same. So let's make it more interesting. Riser, let's delete this one, delete this one, delete this one here. Let's change this one by the way. I will reverse it. It's correct, but simply in general we are adding the value within the condition. In order to make it 3 in 1. Do you know 3 in 1?
Mm.
Nescafe. Let's do it 3 in 1. So if I need to do it 3 in 1, simply here what I will put I, here I will put I, here I will put I. And this will be 1 if VI star greater or equal V carrier. And this will be 0 if VI star less than V carrier. Correct? So this is applicable for what? For all 3 legs. Yeah? So if I is equal to A, I'm generating gate pulse for leg A. If I is equal to B, I'm generating gate pulses for what? For leg B. If I equal to C, then I'm generating gate pulses for what? For leg C. Yep. Good. Now let's discuss the amplitude. This one. How to specify the amplitude and the frequency of the carrier. Now in general, you know that any actuator, in the end of the day, the converter is actuator. Do you remember the definition of the actuator? It's a device to put the control, the process into automatic action, or to provide the power to the process, correct?
That's the exciter, so.
Well, the exciter can be according to the application. So, but the actuator, the meaning of the actuator, I will provide a power to the process. So the car without engine can't move. Yes? Yeah? Here are the same. The machine without a power source, the inverter cannot move. Yeah? So now any control signal has what? Has amplitude, the maximum level. So this, the carrier amplitude will decide the maximum control signal, which means that if VI greater than the carrier, there is no meaning. For example, if VI is equal to 1, if I'm restricting the carrier to be 1, from -1 to 1, let us assume that, let's restrict it from -1 to 1. Then, is there any meaning for VI reference to be 1 or 1.5 or 1.3 or 1.6 or 1.9 or 2? The switch is closed. Yeah? But simply I will not allow to operate higher than the carrier. Why? Because it's a saturation. Do you know the most problem in the saturation is what?
High current.
Sir, very speed. Very speed. High current.
No. This is something else. In terms of control. If the input enters to saturation, yeah, I am above the maximum current, maximum control signal. Yeah. Now the control will do what? Will try to react. Yeah, the control will try to react. It will reduce, for example, the injected reference. Yeah, nothing will change. So this will be lost in translation. Yeah, it will be very dangerous. It enters saturation, nothing can be done. Yeah, so simply this means that the amplitude of this one must match the maximum amplitude of this one. If this one is normalized, then I will normalize the carrier. The frequency of the carrier will decide what?
Harmonic content. Harmonic content.
Yeah, it will decide the harmonic content. Which harmonic content? In general, for the inverter, we have what? We have conduction losses and we have switching losses. So if I'm increasing the switching frequency, I'm increasing which one?
Switching losses.
The switching losses. But I'm reducing what? The conduction losses. Yeah? This is in terms of the losses. But this one will decide something very important. The speed of the controller. In the end of the day, the controller signal will be carried over this carrier, correct? Yeah? In the end of the day, if I need to implement this one in hardware, I will use what? DSP or microcontroller. Yes? Or computer. Yep. Now simply here, I need to use what we call the sampling time. I'm reading the input, I'm calculating whatever I need, I'm refreshing the output according to what? To a sampling. Yes? So this also will decide the sampling time. Yeah? In the end of the day, or it will decide when you will refresh the output. Yeah? So the frequency of the carrier decide the bandwidth of the current control or the controller engine. Good. What else? Do you have any question?
دكتور ليش حطينا مثلا يعني ثيتا من اول؟ مش اصلا كان عندنا اوميجا؟ ليش ما نحط مثلا اوميجا تي او وخلص؟ اللي هي ثيتا يعني بس انه
Okay, we have omega. That's a good question. T from where will?
integration.
From where T? Huh? So T for you is before 1 minute. For me, for 2 minutes. Huh? So from where T? The integration. Yeah. Thank you. Yeah? Some will say that I will inject T. From where? Yeah. Yeah? Okay. Now, if you don't have any question, this will be a short exam for you. يلا الورق. Plot the flux of the machine under constant V over F control as a function of the frequency plus the normalized. Okay, plus the normalized flux of the machine under constant V of F control as a function of the maximum frequency if the voltage source inverter is providing F between 5 Hertz to 150 Hertz, knowing that F rated is equal to 60 Hertz. So this will be 6 and this will be 120. Normalized. Do you know the meaning of normalized? Normalized flux. So plot the normalized flux of the machine under constant VLF control as a function of frequency if the volt source inverter is providing a frequency between 6 Hz to 120 Hz, knowing that the F rated is 60 Hz. 5 minutes. كل نقل السؤال صح؟ اوكي اطلع اساس نقل السؤال الكل.
بس مش فاهم انا ايش بالضبط الفكرة.
I need to plot the normalized flux of the machine from F minimum to F max. I'm using constant V over F.